This is part two of the mole conversion lecture. Um, in this part, or in this lecture, we're mainly going to be looking at conversions that involve molar mass. So remember, molar mass is the mass of a mole, and it's in units of grams per mole, and we can write it as a conversion factor where 1 mole of whatever the substance is equal to the number of grams of that substance. So remember that if it's a compound, you have to add all the atomic masses of the elements that are in that compound together. If it's just an element, you just look up the atomic mass off the periodic table. We can also use it as a mathematical formula if you need that as a crutch to help you figure that out. If you're looking for the mass, then it's the number of moles times the molar mass. If you're looking for the number of moles, it's the mass divided by the molar mass. Now, most of the time when we do these, we're going to set them up using dimensional analysis, and that's the best way to learn it, because if you have to use a mathematical formula for everything, there's not one for everything. And so you kind of get in a bind when you have to figure out more complicated problems. Now, these little graphics will help you set up your dimensional analysis. So if we're going from particles to moles, remember that's what we did in part one, we use Avogadro's number. Today, mainly we're going to be focusing on the moles to grams part. So if we're going from moles to grams, we follow the top arrow, so we multiply by molar mass. If we're going from grams to mole, we follow the bottom arrow and we divide by molar mass. Now, these are connected because sometimes we have to go from grams all the way to atoms or molecules. And so if that was the case, then we would follow the bottom arrow, divide by molar mass, and then we'd follow the bottom arrow again and then multiply by Avogadro's number, right? Now, I added a little graphic. This is probably not going to show up in your PowerPoint, but I added this. If we were trying to go from moles of a compound to moles of an element that's in that compound, we multiply by the subscript. And if we have moles of the element and we're trying to go to moles of that compound, we divide by the subscript. Okay? And that also works if you're doing molecules and atoms instead of just moles. So let's look at our first example. How many grams of sodium bicarbonate are in 0.0626 moles of sodium bicarbonate, which is the main ingredient in Alka-Seltzer tablets? If you remember, sodium bicarbonate is baking soda. So we're starting with moles, and we're trying to find grams. So we want to convert moles to grams. And if we go back to our chart, right, we're going from moles to grams. So that means we're going to be multiplying by the molar mass. We're going to use molar mass to do that. So what we're going to do is look up the molar mass for sodium bicarbonate. When we look up the molar mass for sodium bicarbonate, we find that the molar mass is equal to 84.007 grams per mole. Now, that's not very useful when we're trying to do dimensional analysis, so we want to write that as a conversion factor. So the way that we do that is that grams goes with the number, and it's that many grams in 1 mole. So we basically write it as 1 mole of, in this case, sodium bicarbonate is equal to 84.007 grams of sodium bicarbonate. So that conversion factor only works for sodium bicarbonate. So we have our conversion factor. Now we can draw our dimensional analysis line. We start with the number they give us, put that on top of the line with its units. Since we have moles on top, we want moles to go away, so we have to divide by moles. So we take the mole part of our conversion factor, we put that on the bottom, and then the grams part goes on top. And then the moles cancel out. And we're left with grams, and that's what we're looking for. So to solve that, we have to take 0.0626 times 84.007. We're multiplying because the number is on top of the dimensional analysis line. So when we multiply that, we get our calculator answer is 5.2588382. That's a 2. And then we figure out our significant figures. We go back, since we're multiplying, we go with the least number of sig figs. 0.0626 has 3 significant figures. 84.007 has 5 significant figures. So of those two, the least number is 3. So we round our answer to 3 sig figs. We start at the left, count over 3. We're rounding at that 5. The next number is an 8, which is greater than 5. So that 5 rounds up to a 6. And so our final answer is 5.26 grams of sodium bicarbonate. Next problem. We're looking for moles, right? We want to know how many moles, and they give us grams. So we're basically changing grams into moles. So if I want to go from grams to moles, if I go back to my little graphic, right? If I want to go from grams to moles, I have to follow the bottom arrow now, and I'm going to be dividing by molar mass. So that tells me we're using molar mass. And if we're dividing by it, that means it's going to go below the line. Okay, that helps us set up our dimensional analysis. So again, we Google search and we find the molar mass of sucrose. The molar mass of sucrose is 342.3 grams per mole. But written as a conversion factor, it's 1 mole of sucrose is equal to 342.3 grams of sucrose. Again, that conversion factor is only good for that compound. So we start with the number we're given, the 2.85 grams. And since grams is on top, we want grams to be on the bottom so that that unit grams will cancel. So we put the 342 part on the bottom. And that means the 1 mole part goes on top. So the grams sucrose cancel out. And then since the 342.3 is written underneath the line, that means we're going to be dividing by it. So to solve this, we take 2.85 divided by 342.3, and we get our answer to be 0.008326028 moles of sucrose. That should have canceled out. So then we got to figure out how many significant figures. Since we're dividing, it's the same as the multiplication rule. Least number of sig figs, 2.85 has 3 significant figures. 342.3 has 4 significant figures. So that means we're rounding to 3. So remember, leading zeros are never significant, so we ignore those leading zeros. We start counting at the 8. We count over 3 places. 1, 2, 3. I marked that 3rd significant figure. That's where we're rounding it at. So the next number is a 6 that's greater than 5. So that 2 rounds up to a 3. We get our final answer as being 0.00833 moles of sucrose. Our next example, we're given grams of water. And we want to know how many moles. So we're taking grams and we're converting it to moles. So I want to go from grams to moles. So I go back to my graphic and I figure out what do I have to use to go from grams to moles. So if I'm going from grams, I'm going to moles. I got to divide by the molar mass. So we're using the molar mass for that. We look at the molar mass of water. we find that the molar mass of water is 18.01528 grams per mole. Now, if I wanted to calculate that, since water is H2O, I would take the atomic mass of hydrogen times 2 plus the atomic mass of oxygen, and you add that together, you're going to get 18.01528. But to save time on these problems, you can look up the molar mass. So to write that as a conversion factor, it's that many grams in 1 mole. So 1 mole of water is equal to 18.01528 grams of water. And then we set up our dimensional analysis. We draw the line, take the number that we're given in the problem, put that on top. Then, because I have grams on top, I want grams on the bottom so it cancels. So the 18.01528 grams goes on the bottom. The 1 mole goes on the top. My grams cancel out. So to solve this, I take 4.71 divided by 18.01528. And when we do that, we get 0.26148072248 moles of H2O. And then we figure out how many to round to. 4.71 has 3 significant figures. 18.01528 has 1, 2, 3, 4, 5, 6, 7 significant figures. So we go with the least number. Anytime you multiply or divide, go with the least number of sig figs. That means it's good to 3. Leading 0 doesn't count, so we start counting at the 2. We count over 3 places. The next number is a 4, so that means you round down, which means you just chop it off. So it becomes 0.261 moles of water is our final answer. Next problem. How many grams of SiO2, silicon dioxide, are present in 9.0 moles of SiO2? So we're given moles and we want grams. So we're changing moles into grams. So I want to go from moles to grams. So we go back, look at our graphic. If I'm going from moles to grams, that means I have to follow the top arrow, which means we're going to be multiplying by the molar mass. So I'm going to be using molar mass for that. So I'll look up the molar mass. I Google search the molar mass for SiO2 and find that it is 60.08 grams per mole. Now when you look these up, you might get slightly different numbers. That's no big deal. Okay, as long as you write down what molar mass you're using, it's fine. So to write that as a conversion factor, 1 mole of SiO2 is equal to 60.08 grams of SiO2. It's that many grams in 1 mole. So we start with the number we're given, 9.0 moles of SiO2. Since I have moles on top this time, I want moles on the bottom so that the moles will cancel. So I put the 1 mole part on the bottom, and I put the 60.08 grams on top. So my moles of SiO2 cancel. I'm left with grams. That's what I'm looking for. So then all I have to do is solve for that. Since 60.08 is on the top, that means we're going to multiply by it. So we take 9.0 times 60.08, and we get 540.72 grams as our calculator answer. 9.0 has 2 significant figures. 60.08 has 4 significant figures. Because remember, captive zeros are significant. So that means we're going to be rounding to 2 significant figures. So I count over 2 places. I'm rounding at the 4. The next number is a 0, so that means it rounds down, we chop it off. But I don't get rid of that 0. I have to keep that 0, otherwise I'm changing my answer from 500 and something to 50 something. You can't do that. So you got to change it to 540.72 just to 540. That 0 is not significant because there's not a decimal point. This one, there's actually two questions. Solve for the number of moles and molecules in 2.58, my bad. Solve for the number of moles and molecules in 2.55 grams of methane. So we're going from grams, right? And then we have to figure out, well, what can we go to if we start with grams? So I would go back to my graphic. I can go from grams to moles using the molar mass. And then I can go from moles to molecules using Avogadro's number. So we're going to go from grams to moles, and then from moles to molecules. And so grams to moles, we use the molar mass. And then from moles to molecules, remember there's no good abbreviation for molecules, we're going to use Avogadro's number. So we got to figure out the molar mass of methane. So the molar mass of methane, 1 carbon, 4 hydrogens. If we add that together, or if we look it up on Google, we find that methane has a molar mass of 16.04 grams per mole. So if we write that as a conversion factor, 1 mole of methane is equal to 16.04 grams of methane. That'll allow us to change from grams to moles. Now to get to molecules, we have to use Avogadro's number. So Avogadro's number is the number of particles in 1 mole. So 1 mole of methane is equal to 6.022 times 10 to the 23rd molecules of methane. And then from there, we can start. So we're going to use our molar mass conversion factor to do step 1. And then step 2, we're going to use our Avogadro's number conversion factor to do step 2. And we're going to do it all in one dimensional analysis line. We'll pause for a second and get our answer to the first question, which is the number of moles, and then we'll continue on with our dimensional analysis and get our answer for the second part of the problem. So our second question. So we start with 2.55 grams of methane. Since grams is on top, I want grams on the bottom, so it cancels. So I put my 16.04 grams of methane on the bottom. The 1 mole of methane goes on top. Grams cancel out. If I stop right there, that's going to give me moles, and that's going to answer my first question. So I'm going to go ahead and do that. So if we calculate that, we get the answer to question 1 is 0.15897755561 moles. And then we're going to round that to 3 significant figures because 2.55 has 3 sig figs and 16.04 has 4. And so the least number is 3, so we're rounding it to 3. We count over 3 places, ignoring any leading zeros. We count over 3 places. That means our last significant figure is at 8. The next number is a 9, so that 8 rounds up to a 9. Now, that answers question 1. To finish up with question 2, I'm just going to extend my line out. I wrote my answer to question 1 down. I'm just going to extend my line out and then put the conversion factor for Avogadro's number. So since I have moles on top, I want moles on the bottom. So I put my 1 mole on the bottom. I put my 6.022 times 10 to the 23rd molecules on top. And remember, the reason that it's molecules is because CH4 is a covalent compound, and covalent compounds have molecules. So now, plug that in, moles cancel out, that's going to solve for my molecule. So then I take the 2.55, divide it by 16.04, get your answer, and then multiply it by 6.022 times 10 to the 23rd. Or 2.55 times Avogadro's number, 6.022 times 10 to the 23rd, and then divided by 1604, you're going to get exactly the same thing. So when I solve for that, we get our calculator answer as 9.5736 times 10 to the 22nd CH4 molecules. And that's, again, it's going to be good to 3 sig figs. So I count over 3 places. Rounding at the 7, the next number is a 3, so it rounds down, so we just chop it off. Remember, when you chop off, don't chop off the times 10 part. So then we end up with 9.57 times 10 to the 22nd molecules of CH4. So I have my moles and my molecules. I answered both questions using just one dimensional analysis line.